So yesterday we solved this hard LeetCode problem, substring with concatenation of all words. So let's have a look. First we got memory limit exceeded, then we got time limit exceeded, output limit exceeded, and finally my first solution was this one that was accepted. It was very slow. So after some optimizing, we got it to around 800 milliseconds, which is still not optimal, but much better. And we have, so this is my solution. So I do want to go over the idea of my solution, and then since this runtime is just not optimal, we want to get it to here. So I was looking at other top solutions, but surprisingly the number one here, this one, so the idea is really great, but it's really not the most efficient. So I tried out this solution in Python and the runtime is even worse. So this is the runtime for that solution, 4000 milliseconds instead of my 800. Whereas I did find one really efficient and smart solution, that is this one that only takes 80 milliseconds, which is so cool. So it took me a while to understand this because there was no explanation, and it's also got the optimal time and space complexity. So let's go over that. All right, shall we go back and have a look at my solution first? Okay, it disappeared. Okay, so to recap the question, you're giving a string and array of strings, that's words, they are all the same length. So this is a good example here. We have this string, we have this words list. So we are looking at all the subarrays, substrings in S. So it has to be of length 9 because we're making up a substring from words. And permutations means we can do this in any order. So we are looking for substrings in S, which can be bar foo foo, or starting from here, or starting from anywhere that has length exactly 9. So we want to find the substring that is a permutation of all the words here. And we want to return the starting indices of those valid substrings. Okay, so my idea, let's see. So I is going to be the index that traverses this input S. We need it because we need to store that index. And first, we put all the words in a dictionary for constant lookup. So we put them in a dictionary. There is a faster way to do this. We will look at that very soon. But this is the explicit way, which is not the Pythonic way. So if it's not in the dictionary, then we set its frequency. So this dictionary basically is all the words and their frequencies. So if they're not in the dictionary, we set its frequency to 1. We put it in the dictionary. Otherwise, it's already in the dictionary, we increment its frequency. So if we had bar foo foo de, it would have given us 3 keys and the value for food, but would have been 2. So that is setting up our dictionary for words. So when we are looking up, is this word in the words dictionary, it will give us constant lookup time. And this is the special case that I added just to basically take care of the last test case that has all input A's, very long, very many A's, and then the words are just single letter A's, a whole bunch. So the main logic is in here. So we have our starting index I, we have this dictionary of words. Now what do we do? So for J, in the length of words will just be, okay, how many words there are here. So we have 3 words. So J is just gonna go from 0 to 2. So 0, 1, 2. Where do we start? So what are we doing here then? We are taking, since these words are all 3 letters, so we are taking, if we're starting from 0, then we are taking these 3-letter substrings and checking if they are in the words dictionary. So the start index would be I, which is the start index, plus 1, 0, 2 times length, which is just the length of each word, so 3. So it will be first 0 plus 0 times 3, which gives us start index 0. Then it will be 0 plus 1 times 3, which gives us index 3, and then index 6. So the substring we are checking is this part, start until start plus length. So that's the substring we're checking. If this substring is in the dictionary, then we decrement its frequency. So remember, this dictionary is all the words in the words list. So we have bar food, and now we have seen bar, which means, okay, that is found. So we can cross it out, we decrement its frequency, and if the frequency is not 0, then we can safely delete it from the dictionary because we don't have any bar left. So then the dictionary will just have foo and the. And the next round, we have foo, and foo is in the dictionary, so that is also going to be deleted. And then we have another foo, and that is not in the dictionary. So we come in here, it's not in the dictionary, which means that we have now found a valid substring. I don't know why I'm saying subarray all the time. So that means we have not found it. So I have a boolean found here, which is now false. And we can break out of this for loop because we don't need to check the rest of it. And then we can check starting from the next start index. So then it will go into the next round, and in the next round we need a new fresh dictionary again because we are checking against this every single time. We cannot use the last dictionary. So the idea is straightforward. So this is the implementation for it. So this little extra part, which is used just to handle the special case. So let's just have a quick look as well. So if the length, so after we have set up the dictionary, if the length of dictionary keys, so this is gonna return all the keys in the dictionary if there is only one key, which means we just have the same word. In this words, it can be one letter or how many letters, but they are all the same. So they all have just the same key. Then there is no ordering here. So no matter how you do the ordering, it's just gonna give us the same substring that we're looking for. So the permutation of that will just give us that same substring. That's why we can just join everything here into this substring, and we know that is the substring we're looking for. So then for k, that goes from 0 to, again, this entire string s. So this is now the start index in this loop. And end is start plus length is the length of this word times how many words. Well, actually, this is the same length as the substring, so we could actually just use length of substring as well. But this is corresponding to how we are calculating down here with this start plus length times, so the same structure. Okay, but down here we're just checking each word, and here we know there's only one substring, so we know we want to check this whole thing at the same time instead of checking each one of them. So this is substring we want to look for. This is the end index. So before we reach the end of this s, we are doing this. If substring is simply equal to this start and end, maybe like this. So that's the start, that's the end. We're looking at if this part of s is equal to the substring we are looking for, and we were gonna do this for all start index 0, 1, 2 until the end index is reaching the end. Then we have gone through this entire s, and we can return results. So this little part is just a special case. Let's see its runtime. Yes, as expected, it's around 800 milliseconds as here. Yeah, so this was my solution, same solution, around 800 milliseconds. It's not too bad, but it's not optimal. We can have a look at the top solution here. So the idea is similar but slightly different, and then slightly different implementation. So this Python solution here, so what this is doing is that it uses two dictionaries, one for all the words, just like we are doing, and here is the Pythonic way to basically just put these words in a dictionary. We are using the counter from collections. So from collections import counter, and then we are able to just simply put all of these in the dictionary as we are doing here. Count the frequency of each word. And now in these 4 loops, scanning through index, start index I, length minus total length plus 1, so it does not get out of range. So, and we have a default dictionary of integer values. Current word we're looking at is J plus word length. So word length is again just the length of each word. So we are still looking at the full, the bar. So if current word is in the dictionary, then we have another dictionary just called scene. We increment frequency, and once we see that, okay, this current word has more frequency than what we are looking for in the word dictionary, then we know this substring is not valid. We can just break and try the next one. If it's not even in the words dictionary, then it's also not valid. We also break. So then after this, if the scene dictionary is exactly the same as the words dictionary, because we are putting in this, so we're looking at this little subarray of substring, sorry, we're looking at this little substring of current word, and we put all these corresponding words in this dictionary, and if it is valid, it will give us the exact same dictionary as our words dictionary. So if that is the case, then we append result. So very simple idea. I really like the idea, but as I have tried out, we can try out as well. It's not efficient at all. Yes. Yeah, so this was when I was trying it. Great idea, but not efficient. Okay, so now let's have a look at the most efficient algorithm here. Okay, so this does have much better time and space complexity, which we will talk about later. So let's have a look at this solution. All right, we have length, which is the length of each word in the words list. We have word count, which is the words dictionary. I mean, we could rename this to the words dictionary, so we have the same naming everywhere. But again, so this is from collections import counter, so this will just give us that dictionary we're looking for, so we don't have to manually write and add into the dictionary. So this is the dictionary for all the words. Still take this example. All right, so indexes, that's the result that we are looking for. So this part, it took a while to understand, so let's pause that for now. Let's have a look at what's going on inside first. remember this length is only the length of each word. So this is only, so in this case, it's only gonna go 0, 1, 2. All right, so start 0. We have this window that is a default dictionary of integers. So that is gonna give us a dictionary that has integer values, and it will not return key error if that key is not in there. So let's have a look here. Default dict. The functionality of both dictionaries and default dict are almost the same, except for the fact that the default dict never raises a key error. It provides a default value for the key that does not exist. All right, let's keep that in mind. It will come into play later. So words used currently 0. Okay, so let's have a look at this main logic here. So for J in range, this is the starting from 0, and it's gonna go until the last part of it, minus length plus 1. So it's gonna go until here. And it will increment by length, which is 3, which means in this J loop, we are doing first J equals to I, and then J will be equal to 3, and then 6, and all the way until here, because this is length minus the length of S minus length plus 1, so that will give us the last part here. So the word we're looking at will be J, which is the start, and then J plus length. So J plus length, and then J plus length, like this. So if this word is not in this word count, which is the dictionary, if it's not in the dictionary, then we know that substring is not valid. So there is no use looking more. So we put start to be J plus length. So originally it was starting here, now it's starting here. And we reset the window dictionary, we reset the words used, we continue. So let's use this example and go through this, and we will understand what this is doing. So first we have bar. It is in the word dictionary, word count. So in this case, words used is now 1, and window word. So the window dictionary, we put this bar word in there, and then increment its frequency. Well, window of this word, so if the frequency is bigger than the words dictionary, then we know that this substring is again invalid. And what we do here is we take S start so start is currently still 0, start until start plus length. So okay, so we're not there yet, so let's not do that yet. Okay, let's go through this example, that'll be more clear. So first we have bar, which is in the words dictionary, so we do these two. So we're not here and we're not here yet. So then we have also not here. Words uses only 1, length of words is a 3. So then we have full, same thing, word is full, it is in the dictionary, words used 2, we put full in the window, not here. And then now we have another full. Let's see what happens. Word is full, word is in the dictionary, word used is not 3, we increment frequency of full in this window dictionary, so it's now 2. Now we have window word, that is 2, and this is 1 because we only have one full in there. So what do we do now? Window, this is currently referring to bar because we're starting at 0, so S start until the first length. So what it's doing is that it's removing the frequency of the starting word. So, okay, let's see why it's doing that. So we're at full. And we remove the frequency of bar by 1, we decrement, and start goes from 0 to 3. And words used decrement by 1. So it seems like now when we were doing this, we realized that, oh, okay, so this is not valid. Then there's no use looking at anything more. And we also know that whatever that's to the left of this, it will not work. Because if it's invalid here, then we know this is invalid, and we also know this is invalid. If we had more to the left, those are also invalid. So while this full is still having a bigger, higher frequency than what we're looking for, we kind of remove this from our window. So we decrement the frequency of the starting word, and we move start one word to the right. We decrement the words used. So now start is here, and we still have 2 fulls and 1 here. So this is still in this while loop. So we do this again. We decrement the frequency of this word, start plus length. So now there's only 1 full in the window. And we move start again, 3 to the right. So now we're starting at this full. So first it was starting here, then it was starting here, and now it's starting here. And the words used is not just 1. So now we're starting at this, the window starts here, start index is at 6, words used is just 1. So we are no longer in this while loop because they have the same frequency. Okay, so words uses 1, length of words 3, so again we have not found our substring. Interesting. And we continue. So remember the start is now at 6. Okay, so after this loop, where are we with J? We started with I being 0. Oh, we have already gone through the entire J for loop, right? So J just went from 0 to 3 to 6, and when J was 6, that's when we had this while loop going on, and now it's reached the oh, it hasn't reached the end. Okay, J was 6, now J can go to 9. Okay, so now J is 9. Word we're looking at is bar. It is in the words dictionary. Words used is not to. Window, we put that in the window dictionary as well. So has not exceeded frequency. We have full and bar in the current window dictionary, and we have not reached the number of words we want. So currently we have full bar in the window, and starting index is currently at 6. So now we have just looked at J equals 9. Now J equals 12. We are looking at the word is the, it is in the dictionary. Words used now become 3, and the window dictionary now has full bar, the all of them 3, each with frequency 1. So did not exceed any frequency, which means it is valid, and the words used are same as the length we're looking for. So this is a valid substring, and that's why we're appending it to the indices result. We are appending the start index, start there. Now, this guarantees that we have found a valid substring. Why is that? Because at any point, if it was not matching what we're looking for, say before when we had a word that's not in the dictionary, or a word, right now we don't have any word that's not in the dictionary. So here, we will go in there, then we will go into that case. So right now we have only had the case where we have all the words in the dictionary but the wrong frequencies. So the frequency is incorrect, which means it's invalid. If we also had a word that's not in the dictionary, that's also invalid. And when we do find an invalid substring, we move on to the next one, as we have shown here in the while loop. Okay. Okay, so we have now found one substring that is valid, that is full-brother with start index 6. So that is now in the output index. So it's still much left. I'm wondering if I should continue going through this example. Okay, so where are we now? So I is still at 0, remember that. We have not incremented I yet. So J went from 0 to 3 to 6 to 9 to 12, and when J was at 12, when start was at 6 and J was at 12, that's when we have found the first valid substring. Okay, so next one, J is now gonna be 15. Start is still at 6. So the current word we're looking at is full. It is in the word count dictionary. Words used is now 4. And we put this full again in this window. Current window is like this, but now we put full also in the window. So full now has 2 in frequency instead of 1. So we're going into the while loop again. So for full, we are going to remove from the left. So it's start is here. So we remove this full from the window dictionary. We increment start, so we start from the next word. So we remove this, we start from the next word, and we decrement the word used. So now it's 3 again. And we have found another one. So that is gonna be appended to the index. So we have to understand why this is all we need to check that this is a valid substring. So we are the window dictionary and the words dictionary, so they have same length. So the words used is tracking how many words are in this current window. So if the length of current window and the length of the words dictionary are the same, and there are no frequency inconsistencies, because each time we do have something that is more frequent than it should be, we are moving our window and adjusting start index. So this gives us the substring that is valid. Okay, so we are at J equals 15, I believe. 3, 6, 9, 12, 15. Okay, we're almost there with the last one, so let's just go over this. It's unfortunately gonna be a much longer video than I was thinking again. So J just went through all of these 0, 3, 6, 9, 12, 15, and now it's gonna be at 18, and our start index is still at 9. So current word we're looking at is bar. Words used 4. We put that bar into there, so bar is now giving more frequency than we are looking for. So again, we're gonna remove the first bar from this window dictionary, decrement bar, move start to 12. So our current window is here now, starting at 12, words used decrement. So again, we found another one that'll be in the output. Okay, now J goes to 21. It's looking at men. Now it's the first time that we have a word that's not in the words count dictionary. So we are looking at men. It is not in the word count dictionary. What do we do? A better example would have had even more words after this, but we have now seen a word that is not in the dictionary, which means there is really no use in checking. So everything before this, it's just gonna be invalid. It's only gonna be valid. It could only be potentially valid to the right. because we're looking for substrings, so you cannot avoid having that. If this word is invalid, then we can just skip checking starting from foo, starting from bar, starting from man, because usually we are checking like this, starting from that and that and that and that. But now we just get to skip all of those because we have an invalid word. That's why start is gonna jump directly to the next word, which is, so J is at this 21 and it's gonna jump to the next one. If we had more words here, it would have just started from the next word. And we reset the window because we're starting over. Words uses 0, and we just skip the rest of these. We continue to the next J, which would have been pointing at here. So J would have started here to check again. Start would also be here. We have a new reset window. We have the same logic as before, checking for the rest of the S string. Okay, so now we have gone over this really smart solution. This part, we have explained this part and this. Now there is one more question though. Why is it in the outer for loop for I, we're only gonna go until 3 length, just 3? It was very interesting to think about because this is crucial to why this algorithm, this is part of why this algorithm is more efficient than the other ones. Time complexity is different than the other ones. So while we were doing this J loop, what were we checking? We were checking starting from 0, we were checking from 0 and then increment by length, so 0, 3, 6, 9, and so on. So we were checking all the words that are like this. So we have already checked from starting index here and starting index here and starting index here, here, here. So we have already checked selectively all of these start index. Now what are we missing then? Have we checked start index here? No, we have not. And have we checked that? No, we have not. So that's why the outer loop first goes from 0. It's gonna check all of these 3-letter words like that, and then it's gonna go to 1. It's gonna check these 3-letter words, and then it's gonna go to 2 and it's gonna check like this, which will cover all of the starting indices and all of the potential substrings in S. So that explains why this outer I loop is only gonna run from 0 to 2, 0, 1, 2, because we already checking the other indices in here in J. Okay, there was a lot to explain. I really hope I was able to explain this algorithm. Now, let's have a look at the time and space complexity here. Oh, we can also let's just also run this first to show that this is the most efficient solution. Yes, we can see that as before, this is the one that is running in only 80 milliseconds instead of 800, which was my solution, and the 4000, which was the top solution. So this is a very valuable solution indeed. All right, so let's have a look at our algorithm and analyze the time complexity. So we see that here, the outer loop, we are just using length. So length of each word. That's what's K here, length of each word. Now inside in this J loop, so in this J loop though, let's see, with the same example, we are looking at these and these and these. So inevitably we are still looking at every single character in this string. Even though we're checking like this, we are still using this entire string. So that will be linear at least. Let's see, do we have anything that's adding to this complexity? The only extra operation will be here in this while loop, which happens when we have found something like this, and then we just remove this and move it forward, and then we remove this and move it forward. So that, what's the time complexity for that? So let's think. So for each of these little words, it will be added to the words dictionary once. It's gonna be in this window dictionary. So we have this window, the word is adding to the window. And when we find something that's exceeding the frequency we need, that's when we move this window. So what are we doing then? We remove this from this window and we move our window to the right. Remove that from the window, move it to the right. So for each of this 3-letter word, it will be added to the window once, and it can be removed from the window also once. Then it just goes forward. Nothing else happens with that word. So that means even though we are having a little extra here, this entire for loop is still linear, because each word we're looking at in the string will just be added to the window once and removed once at most. So n is length of s, so the time complexity is n times the length of each word, which is this I loop. And why is this better than the other solutions? For instance, I have explained the time and space complexity for my solution. So that is let's see. For I in length of S, for J in, oh, sorry about that. Let's just turn it off. Okay. So I length of S and J length of words. The inside here. we are checking all the substrings. So for my solution, the time complexity would have been the length of S times the length of words. Whereas here, the time complexity is length of S times the length of each word. Okay, memory. M, length of words. Okay, length of each word. Let's see, what are we storing in the dictionaries? Yes, okay. So we have two dictionaries. One is word count, one is window. So so the window dictionary sometimes will go over like here. Okay, go back to this. So as we saw, this window dictionary, once we have found one like this, the next round it will put this full again in the window, but the window will only have at most 3 keys because we have 3 keys in the words dictionary. So even if we encounter one that's longer than what we're looking for, it would just be the same key. So the two dictionaries we are using, at most the keys will be exactly the same as these, and then the frequencies are just integers. So what we are storing in there are simply these words as much as it has. So each of these as a key, and then the frequencies as integers values. So length of words times the length of each word. Yes, so in the entire words. So that's the length of that. Okay, I've been speaking so much. I need breakfast and water. So that's the time and space complexity for this brilliant, very smart solution. And I found it by clicking Python 3, and I think this is the one. Yes, that's the solution. I would like to give it a thumbs up. Where is that? Oh, is the thumbs up button no longer here? That's surprising. Alright. That's it for this hard LeetCode problem. I hope you find this helpful. This is certainly helpful to myself to go over the algorithms and analysis. I will see you in the next problem. Let me know if you have any questions and I'll try my best to answer. Alright.